Hello, friends. MoNaCo here with our last lecture of the year. We're talking about nuclear chemistry and Half-Life. And I'm not talking about the video games from 1999 or Half-Life 2, the video game from 2005. I'm talking about radioactive half-life as it relates to radioactive decay. And the last reference table of interest here is going to be table N, which helps us find half-lives for various radioisotopes. And also, we're going to use a mathematical problem-solving method to determine the number of half-lives that have passed and fractions of the original sample that remain after a given period of time. Our lead-in here is that how long does it take for a radioisotope to be radioactive, like to decay all the way? How long does it take for natural transmutations to turn one isotope into another one? So radioactive activity is a really interesting property. Regardless of how big or small the sample is, the radioactive decay rate is going to be the same. So whether I have 1 gram or 1,000 grams of uranium, they both decay at the same rate. It's a property of the radioisotope. Therefore, the term half-life was invented to describe how long it would take for half of the sample to decay into its daughter nuclides. Since the decay rates are constant for radioisotopes, they can be used in interesting things like carbon-14 dating or radiation treatments for cancer patients. Depending on the stability of the radioisotopes, the half-lives will be different lengths. This gives rise to benefits and detriments alike. So the first thing we got to talk about is what half-life is. And part of the definition was in the lead in there, but radioactive substances decay at constant rate that is not dependent on any other factors. You can heat them up, cool them down, increase the pressure, change the concentration, has no effect. It's still going to radioactively decay at the same rate. It's impossible to predict when an unstable nucleus will decay because it's a completely random process when this happens. The only thing that can be determined is the number of unstable nuclei that will decay in a given period of time, because that's what the half-life is. Therefore, half-life, for the time it takes for half of the mass to decay, is a very important concept in nuclear chemistry. Half-life varies per substance. The table I'm about to show you is in our reference table. It varies per substance because the stability of these nuclides varies. For example, in table N, we see that gold, 198, has a half-life of 2.69 days. So if I had like 10 grams of AU198, then 2.69 days later, I would only have 5 grams because that's what the half-life is. So it takes how long it takes for half of the sample to change. So gold, 2.69 days. Carbon-14, on the other hand, 5,730 years. So if I had a 20 gram of carbon-14, 5,730 years go by, then I'll only have 10 grams of carbon-14. Another 5,730 years go by, I'll have 5 grams, and et cetera, et cetera, et cetera. Each one of these steps is a half-life. A half-life. And while there may be mathematical equations to solve all of these things, we're going to use that stepwise, cutting it in half, cutting it in half, cutting it in half problem-solving method to really get to the root of these things. Some of these radioisotopes, like gold, have a very short half-life. Others have even shorters. Francium-220, 27.5 seconds. Not so long of a half-life now, is it? But other ones, the heavier the elements get, typically the more stable the radioisotopes are. If we look down here at the uraniums, these are the ones that are used in nuclear reactors. So we call this, these are reactor fuels. It will take, let's say we have a uranium fuel rod of 10 kilograms of uranium, we'll call it 233. For it to decay into 5 kilograms of uranium-233, it'll be 1.62 times 10 to the 5th year. So 162, 162 1,000 years for it to decay into 5 kilograms of uranium-233, which is still pretty radioactive stuff, and 5 kilograms is nothing to joke about. So another 162,000 years later, you only got 2.5 kilograms of uranium-233. So half-life for these isotopes that are very long-lived is a dangerous thing, because if we are taking spent fuel rods out of a reactor core, where are we going to put them? Because it's going to be hundreds of thousands of years before they're not radioactive anymore, before they're safe to handle. So that is one of the detriments to having half-lives of so long. One of the benefits is that, geez, this stuff is really useful for a very long time until it radioactively decays. Now, the word problems that we're going to use. Notice here, our reference table T no longer has this formula on it. It's been removed recently. So we're going to have to use a slightly modified type of problem-solving method. We don't have this formula on our table T, so you just have to remember what. Here we go with our chromium atoms. Example, most chromium atoms are stable, but chromium-51 is an unstable isotope with a half-life of 28 days. So T is 28 days. That's how long the time it is for it to decay. What fraction of a sample of chromium-51 will remain after 168 days? So the total amount of time elapsed is 168 days. So you got to think, okay, if one half-life is 28 days and the total amount of time elapsed is 168, the number of half-lives is going to be like this: 168, which is the total time, divided by 28. Let's see, I get my calculator out here. 168 over 28, I'm thinking 6, but I'm not sure. 168 divided by 28, 6. Yep, 6 half-lives have gone by. So if 6 half-lives have gone by, we've had 1 cut into a half, cut into a quarter, that's 1, 2 half-lives, cut into an eighth, that's 3, a 16th, that's 4, a 32nd, that's 5, so 1, 2, 3, 4, 5, and a 64th. 1/64th of the original sample remains. And all I did was I divided by 2, divided by 2, divided by 2 for each half-life as we went. And I counted the number of steps, 1, 2, 3, 4, and divided by 2, divided by 2, to get to 5 total. 1, 2, 3, 4, 5, 6 total half-lives. 1/64th of the original sample remains. Now, if a sample of chromium-51's original mass of 52 grams, what will remain after 168 days? All you really have to do is you take your 52 grams and times it by 1/64. 152 times 1 divided by 64 equals 0.8125. The other way to do it, which is over here in blue, if we start out with 52 grams, we divide that by 2 after 1 half-life. So 1 half-life, we got 26 grams. Then we divide that by 2 again, we got 13 grams. Divide that by 2 again, we got 6.5 grams. Divide that by 2 again, 3.25 grams. Divided by 2, you see the pattern here. Half-life is all about dividing by 2. And after the last one, 0.8125 grams. So each half-life step is cutting the amount of the sample in half. That's really all there is to it. Let's see what else we have to see about half-life in the end of it all. Graphing half-life data is pretty straightforward. A Geiger counter is usually used to detect the radioactivity of a sample, and this is kind of just a picture of what a Geiger counter is. It's a cathode and an anode that relies on the radioactive particle to complete the circuit. And every time a radioactive particle comes flying through the window, blink, it ionizes the argon gas that's in this tube and completes the circuit, and the thing goes tick. And however many times that happens per second, it clicks, and the meter reads how much radiation is coming in. So every radioactive particle that comes in there completes the circuit for a fraction of a second, and it makes the needle dance, tells you how much radioactivity we've got. If you're given a graph and you're asked to determine the half-life of something, it's really actually quite easy to do. You take a vertical line anywhere from one y value to the curve to half of its y value. So if we started out here, there's a y value, 50. We'll drive a line down to half of that, 25. Then we go over, turn 90 degrees, and draw a horizontal line to the curve. This distance, when we read down, this distance is how long the half-life is, 25 days in this particular example. Pardon me. Let's see what else we've got here. Present-day uses of particular radioisotopes. So carbon-14 dating is used to determine for dead fossils or bone that has been uncovered. These types of things tell us how long ago the sample particularly died, and it looks at the ratio of carbon-14 to, I think, carbon-12. It's a reference. So you compare the two ratios, carbon-14 to carbon-12, and you can tell how long ago something died, which is useful if you're trying to do archaeology or discover things about, mummification or any old dead sample that contained organic material. Uranium-238, this is actually used in a couple different places. Nuclear energy, so we can fission reactions to make electrical energy. Another isotope of uranium is also used to date rocks, dating of rocks. So how old is this rock? We'll do some uranium dating on it to figure that out. And in that case, they use the uranium to lead ratio. So the U-238 to Pb-206 ratio. You compare how much of each of these isotopes you have in your sample, and you can tell how long ago that rock solidified from magma here on planet Earth. At this point, you should have a basic definition of what radioactive half-life is as it relates to radioactive decay. Remember, always dividing by 2. You should also be able to look at table N to find those half-life times for various radioisotopes. Those are the ones that will be on the tests, quizzes, Regents exam. And then using that mathematical problem-solving method to determine the number of half-lives that have passed and the fraction of the original samples that remains after a given period of time. There's a bit of practice on this, page 13 through 16. We have a prep and a quiz for you online as well, and that's all there is to the lectures this year. All we got to do is practice, 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 and prepare, prepare, prepare. Thank you very much for your time.